This video is the first in a series showing you how to use CrystalGrower without the graphical user interface. So there's a few options for running CrystalGrower without the user interface. You can run it through the terminal, if you're familiar with the terminal, or you can just run it as a standalone executable. But there's a few files you need to be familiar with before you can run simulations without the user interface. These files are all set up behind the scenes when you fill in the boxes in the user interface. But if you're using the terminal or executable version of CrystalGrower, you need to be familiar with manipulating these files manually. So we need to open these files with a text editor. I prefer to use Notepad++ on Windows, but there are similar text editors on Mac and Ubuntu systems. Or if you're familiar with the terminal, then you can open it with text editors from within the terminal. I'll cover examples of these in the next video. So the first file we're going to look at is input.txt. So this contains pretty much all the important parameters that CrystalGrower is going to need to actually run the simulation. And a point to make here is that input.txt and net.txt, which we'll come to later, have to be in the same folder as your CrystalGrower executable. If they're in any other location, CrystalGrower won't read them and you'll get an error. It's hardwired to look in the same directory for files with these names. So now I'll open input.txt and have a look at the contents of the file. One of the reasons I like to use Notepad++ is it has quite an intuitive user interface, and it has a lot of extra functionality compared to just Notepad or WordPad, which you'd normally use on Windows. You can record macros, so if you have to do something repetitive, you can record what you're doing and just play it over and over again, which saves you quite a bit of time. And you can also install plugins which give you even further functionality. For example, I've installed the Compare plugin, which lets me compare the differences between two text files with a few button clicks. So now let's quickly go through this file and explain what each of these lines mean. So each of these parameters has a prompt further down in the file, explaining what each one means in a brief line of text. So this first line here is the directory to store data. So this will be where your simulation output is saved. And this path is defined relative to the location of your input.txt file. So if I go into my folder, my input.txt file is here. If I go into simulations, tutorial, this is where it will save my output. You can see I've already run a simulation here. So if we go back to our tutorial directory, back to our input.txt file, we can move on to the second line. This is the file root to store data. This is just the root name that your simulation is going to be assigned. So everything's going to be called 1_Bidentate_tutorial, followed by the suffixes explaining which type of file the output is. So a count file would have the suffix _count.txt. Then we move on to these next three parameters here, which are related to checkpointing files. So you may be familiar with this from using CrystalGrower with the user interface. You can use the endpoint of a previous simulation as the starting point for a new simulation. So the first question is, do you want to load a checkpoint, yes or no? So if you say yes, it will look for a checkpoint file to load. If you say no, it will not. That then leads into this fourth parameter, which is the path to the checkpoint file. So again, you need to define a file path similar to what you did in the first parameter here, but this is to the checkpoint file. And this is again relative to the location of your input.txt. So for example, if I wanted to use the checkpoint from my previously run simulation, I'd go into simulations, tutorial, and I'd pick this checkpoint file here. So I would have to say it's in the directory tutorial, simulations, tutorial, and the file name is 1_Barite_tutorial_checkpoint.txt. But my input.txt is located in tutorial, so I can just write /simulations tutorial. Now if we go back to line number 5, this is, do you want to save a checkpoint at the end of your simulation? So if you say yes to this, then it will automatically save a file at the end of your simulation and give it the suffix _checkpoint. This can lead to the end of your simulation taking a little bit longer, especially with large simulations or ones with lots of internal defects. So you should choose wisely when you want to use this feature. Then we come to one of the most crucial lines in the file. This is the path to your structure file. So this file is really important because it contains all the information about the crystal structure that you're going to grow. So all the connectivity, all the neighbors, and all the unit cell information about the structure that you're going to grow. So you have to ensure that this line is correct. So this is again a file path relative to the location of input.txt. So if we go and look for this file now, it's in my structure files folder, Ionic, and it's called barite.txt. So let's find that file. So at a glance, it can be quite a complicated looking text file. I'm not going to cover this in detail, but there are lots of guides on our website explaining exactly the format of these files. And you can either generate these through Topos Pro, or you can use Crystal Maker and the interaction program for CrystalGrower. So let's go back to our main directory and our input.txt again. So now we can move on to line number 7. So this is one of the lines where you decide some behaviors in your simulation. So the prompt here says normal / growth modifier / ordered. If you set this parameter to normal, it will just run a normal simulation without any extra features. If you say growth _ modifier, then you've enabled the addition of growth modifiers to the system. So these would be molecules that stick to your surface and slow down crystal growth in certain sites, also called poisoning agents. If you use this option, then there'll be additional questions at runtime when you run CrystalGrower. Similar to when you use the user interface and you click this option, an extra tab appears when you assign additional parameters. A similar thing will happen when you run CrystalGrower in the terminal or executable mode, but these questions will appear just as the simulation starts to run. You can also respond with ordered to this question, and that will enable the ion ordering feature in CrystalGrower, designed for aluminophosphates or zinc phosphates in tile-based systems. Then line number 8, we go to another parameter which can control the behavior of the system. This is the addition of a screw dislocation. So if you say no to this, then your system will grow without a screw running through it. If you set this parameter to yes, then you can input one screw dislocation running throughout your structure. And you define the direction of this core, the translation at the core, also called the Burgers vector, and the location of the screw core running through your crystal if it's not going directly through the center. But we'll cover that in another video. Then we go to line number 9, which is how many checking sweeps the simulation will run. This is designed to look for internal defects, so if you're really interested in the internal defect structure of your material, then you should set this to 2, as it will do an additional sweep for neighbors to ensure that the defect structure is correct. If you're not looking at your defect structure, then you can leave this as 1 because it can extend the length of your simulation, but it's very important to set this parameter to 2 if you're looking at internal defects in any scenario. Then line number 10, another 1 or 2 answer. This is involved with calculating the combinations of site types for your crystal structure. Generally, you should just stick with number 1 unless there are problems, then you can switch to 2. Then line 11, this is another very crucial parameter as it decides how your crystal structure will be partitioned. So you can respond with either tile or net. Net will treat your structure as a simplified net, for example, ionic crystals or molecular crystals. And tile will partition your structure into natural tiles. So this is designed for framework materials such as zeolites. MOFs should be treated as net crystals, even though they are framework materials, as they're made up of molecular building units. Then we move to line number 12, which is, do you want to calculate the required memory for your simulation? If you respond yes to this, CrystalGrower will calculate the required memory for your simulation. If you say no to this, then you assign the dimensions of your memory requirement to yourself, and this happens at runtime. Then line 13, what is the maximum memory in megabytes that you wish to use? This is more of a safety option. CrystalGrower will not ask for any more memory than this line here. So currently I've got it set to 10,000, so that's 10,000 megabytes, so 10 gigabytes roughly. That's way too much, but this line isn't too important unless you've got a very strict memory requirement on your computer. Then line 14, the temperature in Celsius in your system is quite self-explanatory. Then line 15, if we scroll down a bit, we can see this is the number of iterations. So an iteration is one loop around the program's main loop, which is one growth or one dissolution event. So this is tied to your simulation length. So here I've got it set to 1,000,000 iterations. So that's 1,000,000 growth or dissolution events. Then we move to line 16. This is the delta mu mode that we want to assign to our simulation. So if you've used the user interface, you'd be familiar with the diagrams showing the profile of delta mu versus iterations. And in this case, I'm using mode 5. So at runtime, it will ask me for some extra information for this mode. how long I want to run at high supersaturation, which is defined later in this file, and what my next delta mu or supersaturation is going to be in kcal per mole. Other modes will ask for a different set of questions, similar to the different tabs in the graphical user interface. So these next two questions are also related to the delta mu, also called the thermodynamic driving force or the supersaturation. Line 17, do you want an excess supersaturation of any component? So if you set this parameter to yes, at runtime you will assign an excess driving force or supersaturation to each of the components in your system. For example, in a MOF, you would assign an excess to your solvent because it's constantly in excess. And then you can play around with an excess of linker or an excess of metal to get different crystal morphologies, depending on what you used in your experiments. Line number 18 is the starting delta mu. So this will be the driving force in kcal per mole that your simulation will start at. Then we move on to the 6 parameters that define the data output frequency for the simulation. So lines 19 to 21 are related to the simulation output where you actually visualize your crystal structure. So line 19, the number of frames for your movie. So if you only want 1 frame at the end of your crystal growth, then you would set this to 1. But if you wanted to watch your crystal grow over time, then you would set this to greater than 1. Line 20 is the number of iterations at which the movie capture starts, and line 21 is the iterations at which the movie capture ends. So movie frames will be spaced equally across this range of iterations that you provide here. So in this scenario, it's going to capture 1 frame right at the end. If I set the number of frames to 2, it would capture a frame right at the middle and right at the end of the capture window. Then the next 3 parameters, we have a similar set of options for the numerical data output by CrystalGrower. So line 22 is the number of data points that you can plot on a graph. And then lines 23 and 24 are the start and end capture window for these data points. So you can decide when you want to capture data again. If you're only interested in the last half of the simulation, you can just change this first number here. If you're only interested in the first half of the simulation, you can change the second number here. Then the final 2 lines in the input.txt are related to the coloring of the crystal. So line 25, do you want to visualize crystal terraces? If you say yes, then you'll be given the options to identify the facets in your grown crystal. If you say no, it'll only be colored by species type. So barium or sulfate, they'd just be assigned 1 different color each. And by responding yes to this question, you then are given 2 options when you run the simulation at runtime. You can either type find to look for the facets, or you can type color to use a facets file that you've already generated. And the response to color will then read this line 26, which will be the path to the file which contains those facets that you've already generated. And this is again defined relative to the input.txt, the same as all the other file paths. So now that we've run through input.txt, there's still another file that we need to look at before running the simulation. And that's because we're running our simulation in net mode. Running a simulation in net mode means that we need to assign energies to the interactions between the nodes in the net, so our molecular interactions or our ionic interactions. In the graphical user interface, you assign these energies in a separate window once you've declared that your file is a net file. But without the graphical user interface, we need to change this file manually. But we'll still have a starting point generated from Topos Pro, so you don't have to make this file from scratch. So let's open that file and have a look at its format. Again, there's a very detailed description about the formats of all these files on our website in the manuals section. So some of these lines look quite complicated, but CrystalGrower is only using a part of them. The rest of the lines are labels to help you figure out which interactions are which. These numbers before the colon here are the interaction types. So you can see we've got 7 interactions, we've got 7 lines, and there are 5 interaction types because 2 and 3 are doubled. These are the interaction types based off of the molecule or ion's point group. Provided the ions are related by symmetry, these interaction types should be the same for each of the same ions. If their coordinations are slightly different, then these will not be the same. They'll be different because their point groups will be different. So after the colon, we've got some label information. 1A shows you the simplified net node that's used as the center of the species. So in Topos Pro, this will be ZA1. The A denotes the chemical species and the 1 denotes the symmetry of the species. So if it's different chemically, it'll have a different letter. If it's different by position or coordination, then the number will be different. Then we've got the origin species from which this interaction originates, and the destination species, so the one that it bonds to. So this is going from a sulfate to a barium, and the numbers again are related to the point group of the species. So if the connectivity is different, so you had a sulfate with different number of bonds coming off of it, then this number would be different. Then there's a unique symmetry label, which will be different for every bond, which helps you locate which bond it is. And then you have a bond length, which also helps you locate the interaction type. This is repeated for all the interactions originating from each species. And then we get to the lines which you would be manually editing, which is the energy assigned to these interactions in kcal per mole. So here, interaction type 1 has an energy of 1 kcal per mole, and that is the energy cost to replace that interaction with an interaction to solvent. So these are the numbers that are actually being changed when you're using the graphical user interface to give different energies to your interaction types. And the convenience of the user interface is that it changes the corresponding interaction on all the related molecules or ions. So if you change this energy here, interaction type 1, on species 1A, it will also change it down here, because this species is also 1A. If you move to the end of the file, you'll see that the other species in the file are 1B, so these will be treated separately, although currently I have them with the same energies. But you can see this is the reverse interaction, the barium to sulfate interaction. So now that we've set up our input.txt and net.txt, we can actually run our simulation. So our simulation is just going to be a test simulation of barite without any extra features like screw dislocations or growth modifiers. We're just going to use some energies that I worked out earlier in our net.txt file. So let's actually run the simulation. So you can either just double click the executable, or you can execute it through the terminal, which I'll cover in the next video. There are some shortcuts using the terminal, which is why I'll cover it separately. So if we double click the executable, the program will start to run and we'll get some additional questions. So whenever you're using a net file, it will always ask you this question: do you want molecules grouped, yes or no? And this is related to the point group symmetry that I discussed in the net.txt file. CrystalGrower requires all files to be in P1 symmetry in the primitive unit cell, because crystal symmetry is broken at the surface. But because the interactions are symmetrical on each molecule defined by the point group, then we can group things that are related together. So in this case, we're looking at barite. We've got barium sulfate. All of the bariums have the same connectivity, and all of the sulfates have the same connectivity. So we can group them together and reduce the number of species we need to consider from 8 down to 2. So 4 sulfates, 4 bariums. We can reduce that down to 1 sulfate, 1 barium by saying yes to this question. If you want to consider things like chirality, then you'll need to respond with no to this, because chiral species would be recognized as the same, even though they may grow differently. This is another follow-up question which only appears when you have a net-based structure. An important point to note here is that these questions that appear at runtime are all dependent questions on answers that you've given in input.txt. They're not required for every single simulation, whereas all the parameters in input.txt are required for every single simulation, regardless of what structure you're looking at. And this question here is related to assigning different energies to monodentate versus bidentate interactions. So if you have an interaction from one center going to multiple centers, or from one center to one center. So to keep it simple, in this case we'll just say no. Then we have to assign parameters for our delta mu mode. So I've picked mode 5. I'm just going to set it slightly above equilibrium at 0.5 kcal per mole. And the number of iterations at the starting delta mu for mode 5, I'll just say half the simulation, so 500,000 iterations. And then this is our coloring question. So do we want to find surfaces or color surfaces? As we haven't found surfaces before, we'll do find here. Then the simulation will start. It'll give you some information about the memory it's going to use, and you'll get a progress update every 100,000 iterations. Once the simulation finishes, if you run it by double-clicking the executable, the command window will close, which is another benefit of using the terminal, as it keeps the window open. So if we go to our simulations folder, tutorial, we'll see that all our files have been overwritten, and we can visualize our simulation output in a Veto or with the CrystalGrower visualizer. If we open the structure in a Veto, you can see the surfaces have been colored according to their layer type, and this is controlled by the facets found file that is generated. In the user interface, you can change the layers that you want colored directly through the user interface. But similar to the net.txt and input.txt files, when you're using CrystalGrower through the terminal or as the executable, you have to edit the file manually. So let's have a look at the structure of this file. This is the last file that you need to know how to edit if you're going to use the terminal version of CrystalGrower. So let's open this file. So I'll briefly explain the format of this file. There is a detailed description on the website and in the manual. First line up here is the number of facets to color, so in this case it's 16. Then you've got 3 parameters here which define the vector coordinates for the direction of the plane, and these are scaled based on the unit cell parameters, which are themselves scaled to the length of A in the unit cell. Then you have your D spacing for your planes, which you know from X-ray crystallography. So those first 4 columns you don't really want to change at all. Then we move on to columns 5 and 6. These are the 2 columns that you might actually have a reason to change. So column number 5 is the number of layers that you want to color on that facet. In this case it would color 4 layers down from the top layer on this facet. Then you also have the offset for the layer. So if the spacing between the colored layers is correct, but it's slightly coloring the layer below or the layer above incorrectly, you may have to apply an offset to the slice that defines the boundaries of the layer. This can happen for many reasons. For example, if your species don't perfectly lie in a line along that plane. This happens a lot for tile-based structures when parts of the tile are either displaced above or below the plane. CrystalGrower usually finds too many facets rather than too few, but if you are missing certain facets that you know are in your crystal structure, maybe you need the planes that are halfway between the planes that CrystalGrower has found, you can find these in the facets all file. So if we open that one, you can see that it has all the planes from -4, -4, -4, all the way down to 4, 4, 4. So you can cut planes out of this file and paste them into your facets found file. Just remember to update the number of facets in the file if you do this. We can see here that 16 facets have been identified, whereas in the simulation output we can only see about 6 faces. So we can try and reduce this down to 6. And the way we reduce this is by deleting facets from this facets found file. But first of all, we should always make a copy if we're going to edit anything. So I'll save this as a copy, which I've already done previously. And we can open that copy and start editing it. So we know there are only 6 facets in the crystal really, so we can try and delete some of the ones that we don't need here. So we know from experience that barite is an orthorhombic unit cell, so the planes can be a little bit easier to identify. So if we look at the morphology, we can see that running along the Z direction there are 2 planes there. So that can be our 0, 0, 1 plane. You can't see, however, a plane running along the X, which would be the 1, 0, 0, which is picked up in the file there. You can actually see it's colouring in from the corners, which we don't want. So we can easily remove those ones. So let's remove the 1, 0, 0 and the -1, 0, 0. And whenever you remove a plane, you have to update the number of planes in the file as well. So we'll set that to 14 to keep track of how many we have left. The second thing we can see is we've got 4 planes of the same set here. The 2, 1, 0 set with the same D spacing. And that should correspond to the 4 edges that we have around the plate. So we can hold on to those. But the 2, 1, 1 planes, there's only 2 of those. So we can probably get rid of those ones as well. So that takes us down to 12. So now we need to get rid of another 6. And we can see that there are lots of higher index faces along the same orientation here. We only need a pair of those planes, so we need a top and bottom face. We know that they're along the 0, 0, 1 direction. You can see from the crystal colouring that multiple layers are being assigned the same colour. So that probably tells us that the 0, 0, 1 is a bit too high. But the 0, 0, 2 might be okay. So we'll get rid of everything except the 0, 0, 2 and the 0, 0, minus 2. Now we've reduced down to 6 planes, which is what we need. We can also edit the number of layers in this file, so if it's not colouring every layer on the facet, if there's a lot of nucleations, then you might want to put this number higher than 4. And we can also edit the offset. So let's now run a simulation using this as our new input and see if we've tidied up the result. So we need to go back to our input.txt. We'll call this simulation number 2 to stop from overwriting our previous one. And we need to update the file path for our colouring file. So we know it's in the same folder as the simulation output. So we can just copy and paste that file path there. And then we need the actual name of the file too. So we'll copy and paste that as well. Save that input.txt. And then we can run our simulation again. And then respond with the same answers to the questions that we get. So yes, no, 0.5, 500,000. And this time we'll say color because we've already found the facets. And we'll let the simulation run. So now that our simulation's finished, we can visualize the result in Avito. So we'll open 2 Bidentate this time. You can see we've tidied up the edges of the crystal. And the top layers are now correctly partitioned. So you can see I haven't coloured enough layers on the top here, as 2 of the bottom layers aren't coloured in the same format as the 4 top ones. But it shows that the 002 was the correct choice for the layer colouring on top. So that was just a crash course in how to edit the files when you're using CrystalGrower through the terminal or through an executable, and just a basic simulation with some layer colouring. In the next few videos I'll show you how to change your free energies of crystallization. Then I'll show you how to implement extra growth features like screw dislocations and growth modifiers. Then we'll progress into showing you how to use the terminal and how to use HPC clusters, such as Condor or the CSF at the University of Manchester.